about.
Okay, hello everybody, welcome back. This is day 2, and our first lecture is by, he's writing it up, Shengxuan Liu, and he's going to tell us about stability conditions of X24 in P5.
Yeah.
Sorry, quick thing for people in the people watching remotely. If you have any questions, if you could post them in the chat. We don't have sound from the call because it will cause feedback with the mics. So you can post any questions in the chat. If you shout us, we won't hear you.
Okay, thank you very much. And I will talk about the stability condition of S24 inside P5, which is the same title I read online, but easy to write it down in short words. Okay, all the things I will work out today will be overseen, and all the variety will be smooth and projective. So first part, I will give some background on the stability conditions. For the stability condition, the most easiest case will be curves. So we will try to do some traditional things on curves. So for curve, then let's see your curve.
Sorry, can you get writing a bit bigger?
Bigger, okay, sorry, please remind me. Yeah. First, we will do something on curve. So let's see your curve. And F will shift on C. Then we define the slope of F to be the degree of F, quotient rank of F. And we will define it to be in positive infinity if the rank is equal to 0. So there are some good properties about it. The most interesting one will be the existence of the H infiltration. Which means that if we take any shift F, then there exists a filtration such that it has the 0 as the first term, and it will increasing, which equal to F, such that the quotient Fi minus 1 will be semi-stable. I forgot to define the semi-stable. And the slope will be decreasing. Yeah, sorry, I forgot to define what is stable and semi-stable. So let F be a shift. We call F is stable or semi-stable if we have the following property. For all non-zero proper subshifts of F, we have the slope of E is smaller or smaller equal than F. And we'll call it stable or semi-stable. And another property we want to copy from the curve is that if we define the following function, to be minus degree of F plus I times rank of F, then we will see that the image of Z, I should write image out, will be on the extended upper half plane, which means it's the upper half plane union the negative side of the real axis. Now we want to generalize this notation to higher dimensional case, so we will see what we can do. So to move to higher dimensional case, there's a very naive generalization which is called slope stability. So let X to be a variety. F will be a shift on X. Then we define the slope of F to be the Hn minus X is a variety of dimension n. Hn minus 1 times tan 1 of F over Hn times tan 0 of F. Tan 0 is same as the rank, and to be infinity if tan 0 of F is infinity, is 0. Sorry. The good thing for this one is that we still have the HN filtration, but the bad thing is that if we define the function like above, the minus of Hn minus 1 times Chen 1 of f plus I times Hn times Chen 0 of f. And we see that this one doesn't have the image on the external alpha plane. It actually, in putting another way, is that the kernel of this one is not equal to 0, because if you take the skyscraper shape of closed point, it obviously has the 0, 10, 1, 0, 10, 0 if the variety of dimension is higher than 2. Okay, so we want to do something because we still want the information about because for closed point we still want the information about the closed point. So we need to do something to include this part inside. So what we will do is that we define the bridge line stability. Okay. So for bridge line stability, then I will do the other one. Sorry. So for bridge line stability, we will define the bridge line stability. Yeah, please. There should be an ample divisor, so it's a polarized variety. So XH be polarized. Sorry, that's a good question. I forgot to write down what is H. H is an ample divisor. So, then you do the intersection theory. You do the intersection theory. Yeah. X is a variety of dimension. Yeah. So it will be numbers. Yeah, you're welcome. So let's do the bridge line stability. So the idea of the bridge line stability is that we jump outside of the abelian category of coherent shift of X, but we move to another abelian category to A, which is a heart of a bounded structure, which is inside the Dirac category of X. So I need to quick give a definition of heart of a bounded structure. So let A to be a full additive subcategory or inside the bounded Dirac category. Then A is called a heart of a bounded T structure. If we have the following properties. First is that for all the home from larger shift to smaller shift, we always have 0. The second one is that if it has something like HN filtration, means that if you take any object E inside the bounded Dirac category of X, then we have the following filtration. Let me call it a filtration, although it's not a very precise term. E0, then this should be a map. E1 up to En, where En is equal to the object we start with, and we take the cone of them. And similar for this one. And the requirement for this one is that all the AI are inside the heart, and all the Ki will be decreasing. So this is kind of a generalization of the HN filtration property. So another thing we need to do is that the bounded Dirac category is actually too large. So we will try to make it a bit smaller by doing something on lattice. So fix a lattice, finite Dirac lattice. Lambda, and let V to be a surjective map from the Grothendieck group to lambda, surjective group homomorphism. Then we can define the stability condition. There are many equivalent ways, and I will use the way I will use is that giving a heart and giving a stability function. So bridge line stability is a pair where A is a heart, Z is a function, where Z, the function Z is from the lattice to C, such that the first one, yeah. So what we want to do is, yes, so the Z of E will be inside the extended upper half plane, where E is an object inside the D, inside the heart. And the notation E, ZE will means that you take the map to the lattice first, and then you map into the lattice, into the C. You require that everything in the heart is in the upper half plane, extended upper half plane. The second one is that existence of the H infiltration, which means that if we take any object E inside A, I should always write non-zero objects. Then we have the following filtration. And such that I always forget to define what is stable. So for this ZE, we define the slope of E to be minus of the real part of ZE, quotient imaginary part of ZE, and the E is called stable or semi-stable. If we have the following property for all non-zero sub-objects of E, we have the slope of F is smaller or smaller equal than the quotient of E over F. This is just some technical.
Would you draw the upper half plane?
Yeah. Upper half plane.
Draw a picture.
Yeah. So this is C. And the extended upper half plane means everything obviously in the upper half plane. And the extended one means that we have this axis, but we don't have the zero. This is what we mean for an extended upper half plane. Yeah, I don't have the positive, and I don't have zero. Actually, I don't have zero. Yeah, just this part. So I don't have the positive. I don't have zero. Yeah, let's back to this one. And the H infiltration means that EI quotient EI minus 1 is semi-stable. And the slope of them are decreasing. It's larger or equal to EI plus 1 or EI. Yes. And actually, there's a third property, but I don't want to do this here because it is called support property, which is a technical requirement if you want to make the whole theory work, but it is not that obvious at the first place, and it's not central to our talk today. So I skipped the definition of the support property here. Yes. Oh, by the way, the notation here doesn't make any problem because heart is an abelian category. You can show that one. So the one of the inclusion and taking the quotient is well defined. Is there any question about the definition of bridge line stability? So if no, then we can move on. So after giving the definition of the bridge line stability, then one natural question is that when for variety X, when the stability condition exists for variety X, when the stability condition exists. So for this one, we can do some easy things. So for curve, this is obviously right because we can take the heart to be the coherent of the curve, and we take the stability function to be the minus degree of E plus I rank of E. the existence of H infiltration and existence of the images on the extended alpha half plane is obvious by what we recall at the first place. And then we move on the surface. For surface, as we mentioned above, the skyscraper shape of a closed point is inside the kernel of the obviously Z over there. So what we will do is that we will do a tilting. I don't have much time to define the tilting, but I need to define it as I need to use it. Okay, so this technique, this is the technique that the idea is that we try to put the skyscraper shape inside, and the thing is that we define a Tauson pair. So we define T beta to be all the E in the continuum shift of X, such that if you do the H infiltration, the minimal slope of the filtration will larger than beta, and for the F beta we define it in the reverse direction. So after defining this one, then we consider heart A to be given by the extension of, I don't shift the Tauson part. So I keep the Tauson part, but I shift the part of Tauson free part. Sorry, yeah, the total. I do this extension means that everything will be a two-term complex, which you have A0 and H minus 1 term here.
Can you say what's in the brackets of the T beta again? Is this a mu minus or
a mu minus? It means that we take the slope stability and we do the H infiltration, and we take we call the one of the minimal slope. Mu minus means the minimum slope of all the filtration factor, all the H factors.
okay.
Yeah. Sorry, maybe I didn't say it very clear. So yeah, this is a Tauson pair, and you can define the heart to be. So the heart needs to be careful, but let's say that we work on the K3 surface of P-car rank 1. Then we can define the heart that alpha beta to be. I always need to copy this one. Here. Be the minus 10(2) of E minus alpha H squared 10(0) of E plus I times H 10(1) beta HE, where what I mean by the 10 character of you do something means that you use the normal 10 character times E to the minus beta H times E minus beta H. Okay. So one can check that this is really hard, and if you're using this technique, actually you can construct the brilliant stability on surfaces, and this is done by for cases surface done by Brillant himself, and for general cases it's done by Alcara, Bartram, and Bayer Mark III. Sorry.
Why pick up rank 1?
I just pick one. Because I will use this case later, but it can work for any surface. Yeah. There's no restriction on the Picard rank or whether it's case 3 or not. I just will use this case later. Yeah, so I just write this out. Yeah. Okay. So if you run through the proof of written by them, then you'll find that the key ingredient is the traditional Bogomolov inequality. Which means that for a stable shift E, if you define the discriminant, then it is the 10(1) square minus 2 times H2 of 10(0) times 10(2). This one is always larger or equal than 0. And the thing is that we have something information about 10(2) here, so that's why we can use this one to show the stability condition really exists under the 0. The kernel is trivial. If you move to the threefold, then things will be much harder. If you do this tilting, you'll find that there's no information about chain 3. So still, if you take the skyscraper shape of a close point, it's still inside the kernel. But that's not what we want to have. So what we will do is that we will do a second tilting. And I will not write out the second tilting, but you just do the tilting with respect to this slope, and it will work. And to make it work, you still the key ingredient is still a Bogomolov inequality, generalized one. And this Bogomolov inequality will be very, very ugly. And I will write down the cases we will prove. Is that Q00 of E is at 4 times H 10(2) of E square minus 6H square 10(1) E 10(3) E larger or equal than 0. This is the conjecture, and this is the conjecture that this should be hold. If this hold, then you can construct a Bogomolov. You can using second tilting to construct the stability condition. Actually, the real one is that you can construct the Q alpha beta. But Q alpha beta is super ugly, and this is what I will prove. Okay. And if this conjecture holds, then you can using the second tilting to construct the stability condition. And for other method, what we have is that first, if we have a semi-orthogonal decomposition, and if they are in a good relation, then we can glue the stability if we know the each pieces. This would call 2, and second tilting I should call 1. Glue stability. And the third one is that that if you have a curve times the variety x, where x you know the existence of the stability condition, then you can construct the stability condition, and so for the case today is what we will consider is x24 inside P5. So this is a Calabi-Yau threefold. The problem is then you see that if you're using second one, then because it's a Calabi-Yau category, it will have no non-trivial semi-orthogonal decomposition. So we cannot use the second method. If we use, and it is not the cases of the third one because it's not a curve times the surface. So what we will do, actually we use the first one. Yeah. Wrong direction. So I will, due to the time reason, I will only focus on the technique difficulty of the whole paper online. So a quick cut of the method is that if you take x24, what we are going to do is that we take a x224 and we take, sorry, forget. So if we take x24, then we do cut it by the degree 2 hypersurface and cut it again. We produce a curve and we embed it into a K3 surfaces of Picard rank 1. This is a K3, which is equal to S222, which is K3 of Picard rank 1. Then what we are going to do is that first we using this embedding to give a Clifford type inequality. Which means that we giving a slope semi-stable shift C, we will bound it to global section. And then we will using induction each step to get inequality of 10, 2, 10, 1, and 10, 0 on x24. And we will, by a very tedious calculation, we can deduce the Q00 E will be larger or equal to 0 for all the cases we want. Okay. So if you run through this part, you will find out that the difficulty happens here. Is that if we take E inside the tilting heart, yes, and the E is Briones semi-stable. This means that it is semi-stable with respect to all the tilting stability. alpha 0 semi-stable for all alpha larger than 0, smaller than epsilon. Here exists an epsilon for this one. Where the new for new, I mean the stability condition defined by the tilting ones. Then what we want to do is that we want to bound it. We want to bound the global section of this object. We want to bound this one. So to bound this one, what we are going to do is that we use a gamma curve, which will be written in following. So gamma is a curve of 1 minus x squared for x is not equal to 0. X belongs to minus 1/2. And it will equal to 0 for x equal to 0. And this is a function of periodic 1. And for the real gamma curve, we will consider is half of a square, x squared, minus 1 plus x squared. This is the real gamma curve. I will write it on the article. So given the gamma curve, one thing we have is that if you know that you have an object E that is alpha beta semi-stable for some alpha beta of the tilting stability condition, then it must below the gamma curve. So let E be an object such that it is new alpha beta semi-stable stable for some alpha beta inside the region that I didn't write out. Then the pH of E, which is defined to be h1 of E, h squared chen 0 of E, and the chen 2 of E, chen 0 of E is below gamma. So if you draw the gamma curve out, you see that it means that gamma curve is not parabolic, but almost parabolic. And you see that if you take an object E, then this one will be below the gamma curve. And yes, and so the thing is that if we we will get a bounded for the upper half plane is that if we consider, I should write the coordinate out, over h squared chen 0, chen 2 over chen 0. So let's do the general case. So if we have some object E such that the h squared of chen 2 of E and the chen 0 of E, chen 1 over chen 1 of E is larger than 0, and it is not inside the region that near the integral point due to some reason, because it will jump at the integral point. So there's a requirement that it is not near the integral point. So it will be an object here. So what we are going to do is that we draw a line through it, which is 0, and this is the pH of E. And we consider the canonical extension of this one. So we define E tilde shift 1, which is the cone of the home E to the home of E on the OS shift 1. OS shift 1, yes. We consider this object because then this object you can regard it as an extension in another heart, which is this part is E. This part is home E. This is just some multiple of OS to the power n. So at proper stability condition on this line, they will have the same slope and they are semi-stable, and the extension of semi-stable object of same slope will be semi-stable again. So E tilde is semi-stable, which means that E tilde should be also under this gamma curve. So pH E tilde is under gamma. So what we are going to, so next is just a trivial calculation, is that if you take this curve and you calculate the intersection point of this one, then you have that h chen 1 of E tilde of h chen 0, a square of chen 0 of E tilde will be larger or equal than x0, because you need to below this gamma curve. So for this one, you will get a bound of EXT1 smaller than something. And then you using that, the Euler characteristic number is equal to the 2 times rank plus 10(2). And in this case, also equal to the home plus EXT1. You get a bound of the home minus EX1. So you get a bound of the home. And for other cases, you can do similarly. And let me draw a last graph. Is that a very good byproduct of the calculation is this one. So on X24, if you draw it over the plane of H1 or A squared one, H3 of 10, 0, and this one is the 10, 2, 1. Then what you get is that the 10 character of a semi-stable shift will have the following property. It will below this curve. The curve will be look like this one. This is 1. This is 1/2. And this is 1/2. This is 1/32. Which you see that this is better than the Bourgogne inequality. If you do the Bourgogne inequality, what you get is the bound here. Actually, a byproduct of all the calculations run through the paper is that you get a 10 character relation that is better than the Bourgogne inequality. I don't know whether this will produce some interesting calculation in the future, but it is an interesting byproduct to me at least. And I think I need to end the talk here. Is there any question?
That's my job. Are there any questions?
Sorry.
Anyone online, if you can post questions in the chat, because we can't hear you in the lecture room to stop feedback.
I think everyone is lost. Sorry.
No questions? Let's thank the speaker again.
So happy Mid-Autumn Festival, everyone.
So we resume in 10 minutes.
45.
Yeah, 10 minutes.
Yeah.
I'm trying to avoid giving specific time, speaker in different time zones. So if I say in 10 minutes, that's universal, right?
Yes.
Oh, that's sharp. Okay, so it's the Zoom call. The Zoom call is a bit blurred, but the camera image is sharp, so it's the internet connection. Problem, so I can't fix. Is there a team? You break it for
Problem is, if people are coming and they have to be back down here in 9 minutes time.
Is there somewhere I can find a mug and a tea bag? That's all I really need.
Yeah,
Let's do a basic question. Okay, but like,
So patients, you possibly have the experience of talking to undergraduates.
okay.
I don't know.
I've only ever,
I think that's the answer.
I've only ever done like a
Basically,
whiteboard in a
The
small
point
room.
is
Yeah.
preserve and eat.
Big.
Yeah, yeah.
Line, straight lines across the map.
I will do my best.
Give me examples, like in front of what- And you know, you can't get too much information on that.
Somewhere here.
Yeah.
And
Two or
these
three
are
times.
experts.
Okay,
Anyway, I'm just gonna do it.
Okay.
thank you.
So another thing to check. So,
Yeah, even if you take the finite multiple, you take a general projective multiple better. Actually, I don't think so. I think it's wrong. But if you pull back the stability, it will not be so. It may be the weak one, it's not the very one.
Totally. So it seems like maybe a little bit if we were setting up a property.
Hi.
Yeah, Friday should work. How about
Stay out for that.
10 hours?
You get the stats. Well, today was the deadline.
Actually, can I switch that to 11? Does that still work?
Holy moly. Where's our next speaker, guys? It's not here.
No, she's coming back. Yeah, she's coming back.
Let's have a practice session first. You make lots of mistakes. I don't mean mathematical mistakes. I mean, that's just not how you talk. It's not how you practice. So next time you talk, I mean, you know, if Trini was giving this talk, he would be given a full hour.
Yeah.
So it's, I mean, you're at least
Like, sure, yes. And did you use the masters as a way to kind of? Yeah.
Yeah.
I mean,
That's the.
yeah, I mean,
Anne-Sophie will be
yes,
here
so
this afternoon.
I
I don't know. We can ask her. I'll send her a message.
Yes.
Well, just sending notes as they talk to Sarah for the people.
Yeah, no, it was very similar. Like, you have to learn some math and do the thing. But
What the video? Oh, yeah. It was.
precise and it's hard, like it, I find that.
I need you more. No. Patience.
Of course, the camera.
Very worried.
Yeah. What do you want me to talk about?
Here's the microphone.
It's actually testing. You can attach this to yourself in some way. You can take your mask off to give a talk because otherwise you won't be able to.
Is
I
that,
could probably turn volume up a bit, maybe.
yeah, I can, is this loud enough
Actually,
or?
that's fine. Yeah, let's bring out the speakers. We can-
Okay.
that should be fine, yeah. The acoustics is quite good. Okay, so the only thing you need to know, or yeah, there's got a clip on the back, so you can clip it on the.
Yeah.
So that will mean that people on Zoom can hear you.
Awesome.
You should write your number on the wall. And also, so this is the camera doing the Zoom thing. It's focused on the middle board right now. If you move to a different board, you can move it around.
Okay, so it's right to go to this board.
Yeah, I mean, if you're going the wrong way, or if you forget to move it, I will wave at you
Thank
and
you.
say move the camera the right way. Because as I found out yesterday, I forgot to do this like 5 times in my talk yesterday. So it's really easy to forget when you sort of get into the flow.
Yeah.
So I'm watching the Zoom call on my laptop down there. So if you forget to move it or something, I'll give you a wave.
Perfect. Thank you.
Sorry? Okay, that's useful to know. That's really big, actually.
This is actually like the size is pretty good because the internet connection is not terribly great. So it's very sharp on here, but when it comes through Zoom, it's a bit blurred. So that's good of a little.
Okay, right, nice and giant. Okay.
While he's going on the warpath, he's going to go and dig Alessio out of the coffee making. They were like, can we make espresso in 5 minutes? The answer is no. Glad I have an extra tea this morning. These cups are very expensive.
Yeah, it's not satisfying.
Once you take a tea bag out, it's only half full.
Yeah.
Basically like a double shot of weak tea.
Tasty.
Better than no tea, let's put it that way. Oh man, that's just like battery acid. Wake me up.
Please stick up.
Okay, hello everybody, welcome back. So our next speaker of the day is Patience Ablett from Warwick, and she is going to tell us about Gorenstein curves in codimension 4.
Hi everyone. So today I'm going to talk a bit about some work I did with Miles Reed in my master's dissertation. So this is going to focus, as the title says, on Gorenstein curves in codimension 4. So our work follows on from a paper of Schenk, Stillman and Yuan. So in particular, in their paper, they outlined all possible Betti tables for Artin-Gorenstein algebras of codimension 4. So they outlined 16 Betti tables. And so in their paper, they show that there's 8 Betti tables, which, well, I guess this is a first result of Koklin, Golubieski, Kapuska, and Kapuska, but there's 8 which correspond to non-singular Gorenstein-Claviau threefolds. And then there's a second list of 8 Betti tables which do not correspond to non-singular Gorenstein-Claviau threefolds. In P7. And so our work focused on this second list of 8 Betti tables. And so we kind of wanted to populate this list with like concrete constructions of curves. And so in particular, as I mentioned, these Betti tables can't correspond to non-singular Gorenstein-Claviau threefolds. And so that kind of gives us a hint that maybe it would be easier to be focusing on singular curves for our constructions. And so in particular, we focused on constructing stable curves. So in P5. And so that means that we'll have, at worst, nodal singularities. And with omega C ample. And so we wanted to kind of focus on simpler cases, so not cases where we're having C break up into lots and lots of little pieces. So most of our curves are going to be specifically the case where C is the union of C1 and C2, where C1 and C2 are non-singular and irreducible. And we want them to meet transversely in D points. And so from this specific setup, we can get some useful information. So one result of, I think it's actually Hironaka's work from his master's thesis, is that the arithmetic genus of C is going to be equal to the sum of the genus of each of our two curves here, plus the number of points of intersection minus 1. So, and as I mentioned earlier, this paper focuses on Artin-Gorenstein algebras of codimension and regularity 4. So we actually know that C is going to be half canonical. And so that means that 4.
Yeah, what does it mean?
So the Castle-Nuovo-Mumford regularity, I think. So there's a definition in terms of the coherent cohomology, which unfortunately I did not, I should have written down on my notes. Sorry. But that's what we mean there. Thanks. And so yeah, our curve C is going to be half canonical, and so we have omega C equals C 2A, where A is the hyperplane class. Oh, it's on here. Thank you. Great. And so from there, we can get some information on the dualizing sheaths of C1 and C2. So we have that since the inclusion of C1 and C2 into C is a finite morphism of and so we know that we can kind of tell what these homomorphisms are. So we can kind of know what they are from mapping 1 in OC1 to elements in OC2A, which are annihilated by the ideal of C2. And so we have that. And since I mentioned C1 is non-singular, so this equals And so we have some information there about the canonical class. And so we know that where G1 and D1 are the genus and degree of the curve C1. And of course, it's similar for C2. So this is helpful because it gives us a little equation, which I'm going to call star. So that's and of course, the same for C2. And that's going to be helpful for us when we're constructing our curves to know kind of what genus and what degrees are allowed. So I'm going to focus now on one specific case. As I mentioned, there are 8 different Betti tables, but I'm going to focus on one specific Betti table. So I'll just write. Oh, sorry. Hyperplane class. And so this goes on its
So these Betti tables are what? Of graded? Gorenstein?
Yes. Yeah, graded in degree 1.
What is it?
Straight projected space.
That's not a supernatural assumption, but then Gorenstein codimension 4, regularity, whatever. Then it's a theorem that those are the only possible Betti tables.
Yes. So that's in that, I think you're right there. Yeah, that paper of Schenk, Stillman and Yuan. I think it's called Clabby, Gorenstein, Clabby out.
Right.
Awesome.
I was looking at it.
Yes, it's that paper.
So that's a Betti table you're right.
Yeah, sorry, it's a bit wonky.
Does that mean 9 generators and 16
All
relations?
the people who do this
Yes, yeah.
do this.
Yeah.
So
But
4 means there
Yeah.
are 4 quadrants.
Yeah.
The next 4 means that there are 4 cubic visitors.
So
are you looking at the first line?
so these
9
yeah.
is the number of generators. So there are 4 quadrants, 4 cubics, and 1 quadrant.
Right.
Yeah, that's exactly right. So we know from this Betti table, the ideal defining the curve will have.
But 9 by 16 is the thing that you see also.
Yes, but the curve itself belongs to the same component of the Hilbert scheme as the intersection of 4 quadrants, without any cubics there. Right. So the game is the Betti table takes account of the fact.
So this is a highly what's the word? It's a sort of degenerate. So the general component, there is a Hilbert scheme with such a form.
Yes.
And then this is a specialization.
That goes from grow ears.
Yeah.
And so some of the kind of more recent work we've been looking at has been growing from these curves and then using like flat deformations to get back to the Hilbert, so the complete intersection of 4 quadrics in the same Hilbert scheme. So I think Stephen Coughlin recently made some progress on that. We've been working with him also. So yeah, so we know from the Betti table we have 4 quadrics, 4 cubics, and 1 quartic in our ideal defining our curve. And so when we want to kind of figure out what these quadrics are, the like kind of best plan of attack is to look at this top line here. So as Miles said, we have these 4 linear syzygies and then 1 like second linear syzygy. And so we might have more higher order syzygies, but this is like a lot of kind of helpful information. It rules out a lot of different kind of cases of quadrics. And so we can show that here, certainly in the case where the quadrics are monomials, there's two possibilities. So we can have, so I'm going to call this case 1. We can have the quadrics x1, x6, x2, x6, x3, x6. Thank you. So I'm just taking x1 to x6 to be my coordinates in P5.
So you're writing some examples now.
Yes, sorry. So I'm kind of going through this kind of example of how we construct a curve now based on this Becky table.
You have some constructions.
Yeah.
Of curves of this form C1 union C2.
Yes, yeah.
That have that Becky.
Yes, yeah, we do.
We can populate the whole list of things.
Yes, so I won't go through every example.
When you say this is the quadrants, it seems to me that it has a huge number of components because if all those quadrants are reducible, just C1 union C2.
X2, X6, X3, X6.
So
A general point.
So we.
Okay.
So what we're going to get from.
Six is the same practical.
Yeah. So what this Q also it is in the ideal x1, x2, x3 minus the ideal x6.
But sorry, the first ideal is just a hyperplane union
Yeah, so so we know from the first 3 quadrics that we're going to have one curve in a copy of P4 we define by x6 equals 0. And then we're going to have another curve in.
There's a plane curve.
Yes, it's plane curve. Exactly. So that's where x1 equals x2 equals x3 equals 0. So coordinates x4 to x6 here and x1 to x5 here. Okay, I'll just. So going on from this case 1, we know that we're going to have this curve C2, which is a plane curve. So obviously plane curves are non-singular and irreducible, quite easy to understand. It's going to be defined by one irreducible polynomial I'll call f. And further from the Betti table, we know that f is going to be a quadric, cubic, or quartic. And in actual fact, it's definitely going to be a quartic. And so we know this from our equation star, which is on. Oh, that's my God. No, it's sorry. I must write it out again. Yeah, I'll just write it out again. Sorry. So we know from that if, for example, we would have that f was a cubic non-singular, it would have genus 1. And so that would give us a value of D of 6.
Sorry,
but that's
your project space P5, you know it's 0. Go from x1 to x6.
Yeah.
That's weird.
Yeah, it's I think I just started using those coordinates maybe because I was doing things in computer algebra, and then I didn't want to change all my work into different coordinates because I was worried I'd make mistakes. Sorry. Yeah, so we would have, for example, if f was a cubic, that the number of points of intersection is 6, but that blatantly isn't going to work because if we have this irreducible cubic intersecting x6 equals 0 in P2, that's going to be a maximum of 3 points. So we can't have C1 and C2 meeting in 6 points. So
Is this form a star or something that tells you that you have to have 6 points?
Yes.
Yeah, sorry. I'm just looking at this table, sorry.
And so,
So why have we written J equals 6?
sorry, so
Biggest basic approach.
yeah, so if f was a cubic, that would be the case at d equals 6, and then that's a contradiction. Sorry. And so we know basically from equation star just that f is a quartic. That's kind of what we get there. So now we want to think about our curve C1. And so we're going to get to C1 using the curve gamma. So gamma is going to be a curve in P4. Which is equal to C1 union L1. So L1 is going to be the line in P4 defined by x1 equals x2 equals x3 equals 0. And so if our curve, so we believe our curve gamma is Gorenstein, then of course it's codimension 3. So it's going to be defined by the 2n by 2n Pfaffians of a 2n plus 1 by 2n plus 1 skew symmetric matrix. And so we know that according to our Betti table, we've got this quadric and 4 cubics kind of unaccounted for. And that we have the degree of gamma is going to be 13, because this is 12 plus 1. And so that tells us that we're looking at the 4 by 4 Pfaffians of a 5 by 5 skew symmetric matrix. And as mentioned, we want 1 quadric and 4 cubics. So our matrix is going to look a bit like, it's going to look like this. So our skew symmetric matrix, and we're going to have degrees. So we can have, for example, and so our next question in this construction is kind of what are the constraints so that the Pfaffians of this matrix, so that this gamma contains the line L1. And so we want the Pfaffians to all lie in the ideal.
So the ones are the quadratic cube.
Yes, so if you kind of yeah, so and so our constructions there, we're going to use the Tom and Jerry formats of Brown and Reed.
So then we have 5 Pfaffians and 4 are the 4 cubits. You don't have a cubits.
Yes, every cubic's accounted for there. Okay. And so our Pfaffians we can work out are going to look like, for example, and so we have these 2 kind of matrix formats, Tom and Jerry. So I'm going to define Jerry KL to have the element of the matrix Aij in our ideal I, if I or J is equal to K or L. And I'm going to define Tom K as the element Aij in I if I and J are not equal to K. And so you can see with this Pfaffian, the way there's like no indices repeated. And so that means that both of these possible formats lead to all Pfaffians lying in our ideal I. So those are kind of the two possible ways of constructing this matrix. And so So now to construct our curve C1, as I mentioned, this curve gamma defined by the Pfaffians is equal to C1 union that line L1, which was the line x1 equals x2 equals x3 equals 0. And so C1 is residual to L1 in gamma. And this is going to be defined by that quadric and 4 cubics, and then a further quartic. And we can think of the quartic as being defined by the 4 points that C1 and L1 intersect. And so this quartic here is actually going to be the quartic with which we define C2. So we're going to kind of map that into the coordinates of our copy of P2. We can add random terms in X6. And so that's going to define our curve C2. And so that's kind of our quartic ear, if you like. And so quite a lot of our cases are quite similar. Like we've got maybe a curve in C4 with this sort of quartic ear attached. I know in one of the cases we have these 2 quartic ears, so Mars calls that big ears. So the next case is a little bit different. So, sorry. Yeah, so this is going to be Gorenstein and codimension 4 in P5, and that corresponds to the beta table. Yeah. Yeah. So that's residual, as I said, to a line in our curve gamma, and so these 2 curves meet in 4 points on a line.
What did you write there?
Sorry, it's quite messy. It says it's residual to a line in our curve gamma, which was this codimension 3 Gorenstein curve.
Take some standard construction of a curve, for example, that traffic into that matrix, and we force it to have a quartic that we impose a line.
That's fine.
And that line is then a forcing. And we grow out an ear from that. We grow out a plane, that line plus another point.
Yes.
Yeah, and then you make a quartic in there which passes through those form.
Yes.
Sequence points.
Good. And what's the thing with it? So the here is the P2. And what's the thing with 2 years?
So that is one of the other constructions, so corresponding to a different Betty table.
I see. That's so interesting because the ear has dimension 1 bigger than the face or something. That's bizarre, the bizarre organism.
So I'll talk quickly a bit now about case 2. So as I mentioned, this is actually only case 1 for this Betty table. There are other possible quadrics.
So there are other cases for this Betty table?
Yes.
Okay, hold on a second. Because you said that, but then what about the Tom Jerry thing? Because you also seem to be saying that there are 2 ways for that thing to contain a line.
Yeah, so I guess
some
cases within a, yeah. Yeah, we can call that 1A and 1B. And then this is case 2. Oh, sorry, thank you.
Essential difference in terms of geometry because they have different resolution. Sorry, a different structure inside the. Maybe one has some special. I understand.
Makes a difference if you restrict it to the cases, then
It's simply another way to rearrange the same equations.
exactly.
So there isn't 2 cases. There's just case 1. There's only 1 and 1. 2 methods of writing down the equations.
Yeah.
Okay, great, thanks. Sorry.
To
No, it's useful. Thank you.
Talks is that nobody understands, or for 2 people. The second possibility is definitely
no, it's thanks. It's good to have it a bit clearer. So for this second case, our quadrics are given as the intersection of these 2 ideals, so x1, x3, x2, x3, etc. And so that we're actually going to have quite like a nice case here. It's like symmetrical. So we're going to have a curve defined in a copy of.
So you have constructions for all the 16.
So the first 8.
The eight,
yeah, sorry. Yeah, so there's constructions for all 8 cases.
And they are all of this type, C equals C1 and C2.
There is, so the one with the 2 is 3 breaks up into, and like you can kind of show specific cases where they break up into more curves, but we kind of.
Let me ask another question then. Could there be that there is a smooth curve in that genus that has this?
Yeah, so I know in case 2.4, so in Schenk, Stillman and Yuan's paper, they give an example of a smooth curve. Right. So it is possible. So we have a curve here, C1, in the copy of P3 defined by x1 equals x2 equals 0. And our curve C2 in the copy of P3 where x3 equals x4 equals 0. And so, as I mentioned, these curves are symmetric, so they're both going to have degree 8. Oh, that's all. So yes, so we have these 2 curves of degree 8. We're going to define them again using this kind of liaison construction. So they're going to be residual to, each one will be residual to a 3-3 intersection in P3. So our curve C1 will be residual to the intersection F1, F2, where these both lie in the ideal X3, X4. So C1 will be residual to the line I'm going to call L1, defined by X3 equals X4 equals 0 in that copy of P3 I mentioned. And so what we're essentially looking for here is our curve C1 is going to intersect this line, this copy of P1 with coordinates x5 and x6 in exactly 4 places. So write that down.
That's your line L1.
Sorry?
That's your line L1.
Yes.
Yep. So I kind of called it L1 here to kind of show I was thinking about it kind of in this P3, but yeah, this is our line L1. And so we want to intersect our line L1 in 4 places. And then so the trick to this construction is we're going to have this kind of identical curve C2 in a different copy of P3, and we need this C2 to again intersect this copy of P1 in the same 4 places. So kind of got this line and then wanting our curves to kind of meet in those.
This construction is for another Betty table.
No, this is for the same Betty table. So we can see it's got the 4 quadrics, and those 4 quadrics will have the 4.
We've got the 4 quadrants.
Yeah, so we'll have
two independent units defining the curve C1 and C2 residual to them. Right. And then you have a push to look for something to get rid of the line.
yeah, sorry, I was rushing the explanation a bit because I was worried about time, so it's probably less clear than it could be. But yeah, we'll get the 4 cubics from F1, F2, and then C2 will be residual to another like F3 and F4. And then we'll have this quartic defining both C1 and C2. And we'll just have the
So
one quartic.
You lift the cubics on the whole space that are 0 on the other.
Yes.
P3.
Yeah, exactly. And so that's kind of our second case there. And I think this is the one.
The quartic is there. What did you say? To get rid of the line. Because there's still a line.
The residual construction.
And so, yes, so this union of C1 and C2 gives us our Gorenstein codimension 4 curve, again corresponding to this same Betty table here. Great. So I think that's all the time I have time for. Thanks very much for listening. If anyone has any questions.
So you explain to us one of 8 cases, yeah?
Yeah.
Or simply.
Yeah, lots
Why
of.
did you choose this one?
So I like this one because you have these 2 different cases in one case, and I like the kind of symmetric construction. It's quite nice, and the other construction is quite like a nice typical example of what most of our constructions look like.
If there's any questions online, you can post them in the chat. We can't hear you.
So you've got these kind of two like normal forms to have with quadrants. And I think you're getting those because you're informed by that circle top row, by what syzygies could be. Now, those bound to be syzygies for quadrants. But could it be that there are other normal forms which use the syzygies from the 8th guide in the middle as well?
Yes, so I didn't find that in this specific case, but there are, I think some of the other cases in the list, they do have some higher order syzygies just of the quadrics.
So the kind of point where you're, if you like, just short of an absolute rigorous classification is the point where you choose the quadrics. It's now on absolutely rigorous.
Yes, yeah. So once we know the quadrics, it kind of informs us on where we can go from there. And so that's kind of the big question. I think there's still kind of a question of if our quadrics are monomials, are there potentially more cases?
And I'm sorry, you did answer. You said there is a case of a different type of table where you do use the higher order syzygies for the quadrant.
Yes, I can't remember which one it is, but it did have some. I remember one of them did have some higher order.
So just in this case, there is still a lot of remaining products just for this given vesicle. So we have something which is in the same components of the Hilbert scheme as the intersection of 4 quadrants.
Yeah.
So how on earth do you write a deformation where intersection of 4 quadrants, an irreducible curve, breaks off either 2 ears, either one ear like that, or falls apart as two curves like that? And then another question. I mean, Gavin raised the question whether there are more of these cases. And then there's another case about whether the 2 cases patients just outlined actually have a common degeneration. The actual more complicated broken up.
Codimension 5.
No.
No, yeah, sorry. No, different. I thought a different format.
Okay, let's thank patients again.
Thanks.